In this presentation, we will continue our discussion of simple logic gates. Another simple logic gate that we often see in implementation is the NAND gate, or not AND. This is a universal gate, or what we often call a building block. The reason we call it this is that any logic circuit can be implemented with it, and specifically with the proper combination of NAND gates. In terms of conversion, when we want to take a Boolean function and implement it using NAND gates, we need to remember that the Boolean function must be in sum of products form to more easily facilitate NAND implementation. The truth table for the NAND gate, whose graphic symbol is shown here, is basically the inverse of the AND gate. As you can see, the result bit is a 1 in every case except when bit 1 is 1 and bit 2 is 1. In other words, the key case for the AND gate. An alternative symbol that's often used for the NAND looks like this, which looks like a combination of an OR gate and some bubbles here where the inputs come in. This symbol is often called invert OR. This symbol is an alternative to the NAND gate and implements the same functionality. They are often used interchangeably. Here's an example of taking a simple set of logic gates and a simple circuit and converting them into an equivalent form with NAND gates. In this function, xy plus xy prime plus y prime z, we see 3 inputs, 3 AND gates, 2 inverters, and 1 OR gate. This circuit is the implementation of the given Boolean function. If we want to change this to only use NAND gates, our implementation would look like this. As you can see here, the symbols are a little bit different, so let's discuss them. We have 3 NAND gates and a 4th here right before the output. But you also see these bubbles here and here. These bubbles represent negation or complement, however you'd like to say it, and they are often used symbolically to replace what we often see as an inverter or a NOT gate. Another building block is the NOR gate, or NOT OR. Again, any logic circuit can be implemented with it, and specifically with combinations of NOR gates. In contrast to the NAND gate, if you want to take a Boolean function and implement it using NOR gates, it's a good idea to have that function in product of sums form. It makes it a lot easier to implement. And our textbook talks about how to implement different functions using NAND and NOR gates and the rules therein. But if you look at the truth table for NOR, you see that again, like the NAND gate, it's almost the opposite of its equivalent positive gate. In other words, NOR gate, if you look at the result column, is the opposite of what it is for the OR gate. We have a 1 in only one case, when both of the inputs are 0. Just like with the NAND gate, we have an alternative symbol for NOR, and it looks like this. Basically an AND symbol with 2 negation bubbles where the inputs go. Either one of these symbols can be used interchangeably. Here's an example of how we would take a regular circuit that we've constructed and convert it to an equivalent circuit using NOR gates. As you can see with this function, A plus C, or A or C, and A or B prime, and A prime or B or C prime, you would implement that logic circuit in this way, using 3 OR gates, 3 inverters, and 1 AND gate. Now if we make the equivalent circuit using NOR gates, we end up with this. Now here, you have 3 OR gates. Here I've kept the inverter symbology, although you could use the bubbles that we saw in the previous example. And over here, we see the alternative symbol for NOR. The last gate we're going to just take another glimpse at is something we've seen before, and that's exclusive OR. We said before that exclusive OR means one or the other, but not both. Meaning, if one of the inputs is 1, the output is 1. But if both of the inputs are 1, the output is 0. Or if both of the inputs are 0, the output is 0. The algebraic symbol is a plus sign with a circle around it. If we wanted to implement XOR with NAND gates, the circuit would look like this. We've previously seen how to implement XOR with AND and OR gates. But here, you see that we can do it with NAND gates. Remember that NAND gates are a universal building block, and this is a way in which we can construct a circuit using them to implement the exclusive OR function.